fascinating tale of scientific discovery. The existence of atoms was proposed since the time of early Indian and Greek philosophers. According to them, if we subdivide the matter continuously, we will end up with the smallest particle called atom, which is not further divisible. These earlier ideas were only speculative and lacked experimental proof. As a result, the ideas remained dormant for a long period of time until revived by scientists in the 19th century. The atomic theory of matter was first proposed on a firm scientific basis by John Dalton, a British schoolteacher, in 1808. His theory, called Dalton's atomic theory, regarded the atom as the ultimate particle of matter. His theory was able to explain the law of conservation of mass, law of constant composition, and law of multiple proportion very successfully. However, the theory failed to explain static electricity, which was already observed during that period. In mid-1850s, many scientists, mainly Michael Faraday, began to study electrical discharge in partially evacuated tubes known as cathode ray discharge tubes. Cathode ray tube consisted of a glass tube known as a cathode ray tube, which was evacuated of air. Inside the tube, two metal electrodes were placed, a cathode and an anode. When a high voltage was applied across the electrodes, a beam of particles called cathode rays was emitted from the cathode and traveled towards the anode. Faraday observed that in the absence of electric and magnetic field, the cathode rays traveled from cathode to anode in a straight line. In the presence of magnetic and electric fields perpendicular to the path of the cathode rays were deflected by these fields, indicating that they were composed of negatively charged particles. This experiment gave enough evidence to conclude that electrons are basic constituent of all the atoms. The credit of measuring charge to mass ratio goes to British physicist JJ Thomson. JJ Thomson's cathode ray experiment was pivotal in the discovery of the electron. He used a small setup used by Michael Faraday, who discovered cathode rays. The setup consisted of a cathode ray tube evacuated of air, with cathode and anode on either side. When a high voltage was applied, cathode rays moved from cathode to anode in a straight line. His idea was to use electric and magnetic field to deflect the cathode rays and measure the degree of deflection. Thomson applied magnetic and electric fields perpendicular to the path of cathode rays. He observed that the rays were deflected by these fields, indicating that they were composed of charged particles. By measuring the degree of deflection, Thomson was able to calculate the charge-to-mass ratio of the particles in the cathode rays. He found that this ratio was much smaller than that of any known ion, indicating that the particles were much lighter than atoms. Thomson concluded that the cathode rays were composed of negatively charged particles, which he called corpuscles, later known as electrons. This discovery challenged the prevailing notion that atoms were indivisible and led to the development of the plum pudding model of the atom, where electrons were embedded in a positively charged matrix. The charge of the electron was discovered by Robert A. Millikan through his famous oil drop experiment conducted in 1909. Millikan used a chamber with two parallel metal plates, creating an electric field between them. He sprayed tiny oil droplets into the chamber and used an atomizer to charge the droplets with static electricity. By adjusting the electric field, Millikan could balance the gravitational force pulling the droplets down with the electric force pushing them up. This allowed him to measure the charge on individual oil droplets. Millikan observed that the charges on the droplets were always multiples of fundamental value, which he identified as the charge of a single electron. He determined this charge to be approximately 1.602 10 to the power minus 19 coulombs. Millikan's oil drop experiment was a groundbreaking achievement that provided the first accurate measurement of the electron's charge, confirming the quantized nature of electric charge. Rutherford's gold foil experiment was a groundbreaking study that led to the discovery of the atomic nucleus. Rutherford and his team directed a beam of alpha particles, which positively charged particles, at a very thin sheet of gold foil. They observed that most of the alpha particles passed straight through the foil, but a small fraction were deflected at large angles and some even bounced back. Rutherford concluded that the atom must have a small, dense, positively charged center, which he called the nucleus. The deflection of alpha particles was due to their interaction with this dense nucleus, while the majority of the atom was empty space, allowing most particles to pass through unimpeded. The discovery of the proton is credited to Ernst Rutherford. Rutherford further investigated the nature of the positively charged nucleus. He conducted experiments where he bombarded nitrogen gas with alpha particles and observed the emission of hydrogen nuclei. He concluded that these hydrogen nuclei were fundamental particles present in all atoms and named them protons. Rutherford used the non-charged mass ratio of the proton, which had been previously determined by JJ Thomson for the hydrogen ion. By combining this ratio with the non-charge of the proton, Rutherford was able to calculate its mass. The mass of the proton is approximately 1.672 10 to the power minus 27 kg, which is about 1836 times the mass of an electron. The presence of neutron was discovered by the British physicist Chadwick in 1932. Prior to Chadwick's discovery, scientists had observed a form of radiation that was highly penetrating and not affected by electric and magnetic fields, leading them to believe it was gamma radiation. In his experiment, Chadwick bombarded beryllium with alpha particles, which is helium nuclei, emitted from a polonium source. This interaction produced a new type of radiation. When this radiation hit paraffin wax, which is rich in hydrogen, he observed that it knocked out protons with high energy. Chadwick measured the energy of these protons and concluded that the radiation could not be gamma rays as previously thought. Based on these observations, Chadwick proposed that the radiation consisted of neutral particles with a mass similar to that of protons. He named these particles neutrons. The table in the diagram shows three fundamental particles with their properties. The symbols used are E for electron, P for proton, and N for neutron. The charge of proton and electron is same. That is why the atom is electrically neutral. Neutron is electrically neutral. Mass of proton and neutron are almost same, whereas mass of proton is 1836 times that of electron. X-rays were discovered by German physicist Rontgen. Rontgen was experimenting with cathode rays, which are streams of electrons using Crookes tube, a type of vacuum tube. He noticed that a nearby screen coated with barium platinum-cyanide started to glow, even though it was not in the direct path of the cathode rays. Rontgen realized that an unknown type of radiation was causing the screen to fluoresce. He called this new radiation X-rays to signify its mysterious nature. Rontgen conducted a series of experiments to understand the properties of X-rays. He discovered that X-rays could penetrate various materials, including human tissue, but were blocked by denser substances like bone and metal. One of the first X-ray images Rontgen produced was his wife's hand showing the bones and her wedding ring. This image demonstrated the potential of X-rays for medical diagnostics. Rontgen's discovery of X-rays revolutionized medical imaging and earned him the first Nobel Prize in Physics in 1901. The discovery of alpha, beta, and gamma rays is attributed to several pioneering scientists in the field of radioactivity. Rutherford is credited with the discovery of alpha and beta rays. In 1899, while studying the radiation emitted by uranium, Rutherford used an electrometer to measure the ionization of air caused by the radiation. He observed that the radiation consisted of two distinct types, which he named alpha and beta rays. Alpha rays were found to be less penetrating and could be stopped by a sheet of paper, while beta rays were more penetrating and could pass through thin metal sheets. Paul Villard, a French chemist and physicist, discovered gamma rays in 1900. While studying the radiation emitted by radium, Villard identified a third type of radiation that was even more penetrating than beta rays. Unlike alpha and beta rays, gamma rays were not deflected by magnetic fields, indicating that they were electrically neutral. Villard's discovery added a new dimension to the understanding of radioactive emission. Alpha and beta particles are not electrically neutral. Alpha particles are positively charged. They consist of two protons and two neutrons, which make them identical to the nucleus of a helium-4 atom. Because they have two protons, they carry a charge of +2. Beta particles can be either negatively charged, beta minus, or positively charged, beta plus. Beta minus particles are high energy, high speed electrons carrying -1 charge. Beta plus particles, also known as positrons, are the antimatter counterparts of electrons and carry +1 charge. These charged particles are emitted during radioactive decay process and interact with matter differently due to their charges. What is atomic number? The atomic number is the number of protons in the nucleus of an atom. It uniquely identifies an element and determines its position in the periodic table. For example, hydrogen has an atomic number of 1, meaning it has 1 proton in its nucleus. Carbon has an atomic number of 6, meaning it has 6 protons. What is mass number? The mass number is the total number of protons and neutrons in the nucleus of an atom. It gives an approximation of the atom's mass. For example, carbon-12, written as C12, has 6 protons and 6 neutrons, giving it a mass number of 12. Carbon-14, written as C14, has 6 protons and 8 neutrons, giving it a mass number of 14. How to represent an atom using a mass number and atomic number? Atoms are often represented using the notation X, which is superscript and subscript A and Z, respectively. X is the chemical symbol of the element, A is the mass number, total number of protons and neutrons, and Z is the atomic number, that is number of protons. For example, carbon-12 is represented as C12, 6, where 12 is superscript and 6 is subscript. Carbon-14 is represented as C14, 6, where 14 is superscript and 6 is subscript. This notation helps to quickly convey important information about the atom's composition and identity. Now we have a question. What will be the charge and mass of 1 mole of electrons? To determine the charge and mass of 1 mole of electron, we can use the following information. Charge of a single electron, which is minus 1.602 10 to the power minus 19 coulombs. Avogadro's number is 6.022 10 to the power 23, that is number of particles in 1 mole. The total charge of 1 mole of electron is calculated by multiplying the charge of a single electron by Avogadro's number. That gives total charge equal to minus 96,485 coulomb. Mass of single electron is 9.109 10 to the power minus 31 kilograms, and Avogadro's number is 6.022 10 to the power 23. Therefore, the total mass of 1 mole of electron is calculated by multiplying the mass of single electron by Avogadro's number. We get total mass equal to 5.485 10 to the power minus 7 kg. So 1 mole of electron has a charge of approximately minus 96,485 coulombs and a mass of approximately 5.485 10 to the power minus 7 kilograms. How to calculate the total number of electrons present in 1 mole of water? To calculate the total number of electrons in 1 mole of water, we need to consider the number of electrons in each atom of the water molecule and then multiply by Avogadro's number. Composition of water is H2O. A water molecule consists of 2 hydrogen atoms and 1 oxygen atom. Each hydrogen atom has 1 electron, and oxygen atom has 8 electrons, so the total number of electrons in one water molecule is 2 into 1 plus 8 equal to 10 electrons. Now we multiply this by Avogadro's number 6.022 10 to the power 23 to find the total number of electrons in 1 mole of water. Therefore, we get 10 into 6.022 10 to the power 23 equal to 6.022 10 to the power 24 electrons. Therefore, 1 mole of water consists of approximately 6.022 10 to the power 24 electrons. With this, we have reached the end of part 1. We shall continue with atomic model in part 2. Thank you for watching.